lose any power by demanding that there be precisely one terminal symbol. And actually, following Gosset's manner, it just makes it a little bit shorter to write some of the rules. That's all. So it's just kind of a matter of convenience. If you do it this way, if you follow what some authors insist upon being the definition of regular, then you just have a different tree, right? Now you have S goes to lambda. I've replaced only some of those rules, but you still have the other ones there. And then what would I do? Instead of going to ABX, I would just go to AR. And then after AR, I do the one thing you can do from R, which is just go to BX. And then what do I, I've replaced X, I've replaced R with BX, so I still have ABX. And then what do I do now with that X is I just go AR. So one option is I follow the lambda rule, and the other option is I replace X with AR, and then I do the only thing I can do with R, which is replace it with BX, and then etc. Okay, so it's sort of more complicated in one respect, in that the derivations are longer, but it's more simple in some respects because you can say that actually precisely one character of your word is being sort of produced per production rule, which is a kind of a nice property for your grammar to have. Okay. Good place to stop. Oh, bad place to stop. Okay, we're just over the cutoff point, so instead of pausing the video, I'll just push on. All right, that was the basic introduction to regular grammars. Now, let us introduce some more notation. This is just great sort of theoretical computer science notation to have. I think it is kind of complicated and used pretty casually by a lot of people, and so I'm going to try to explain this kind of carefully. Okay, so I'm going to do two things here. I'm going to introduce a notation for strings, and then on the other board I shall introduce a notation for sets. And these notations are very similar, with lots of sort of overloading of kind of characters, but I think they really are sort of two separate things with similar kind of themes. Okay, and I forgot to mention it, but it gets kind of, you might have noticed that there's some sort of, it's very inelegant. The way we have been describing these languages is very inelegant. I keep having to use lots of, comma, dot, 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 and hoping that you sort of get the pattern. And that's just unacceptable. So there's so much recursion going on, we need symbols which are fundamentally recursive to capture what we're trying to express. And so, all right, if X and Y are strings, so give me any two strings, I hereby define some new notation, which is also a string. Okay, so X, Y is the concatenation. Of X and Y. Duh. Okay, so this one's probably you're pretty familiar with. Anytime you see two strings written right up against each other, then that's a new string, which is, okay, I won't say anything else. You know what concatenation is. Okay, notice that X, any string, concatenated with the null string is just X, as is whether you put the null string on the front or the back, it's just X. Okay, that's something worth mentioning. I now introduce a sort of exponent-style notation, which is in some sense totally natural, but it's helpful to do it recursively. So x to the 0 is 0 instances of string x. And so it's just the empty string, or the null string. I keep calling it the empty string. I should try to keep calling it the null string. And what is x to the n? Well, informally, x to the n is just the concatenation of x with itself n times. But let's just define it recursively as the concatenation of x and x to the n minus 1 for n greater than or equal to 1. So if you're trying to pretend that you don't know what that means, to concatenate n times, then okay, it just means that. This is a recursive, fundamentally recursive definition. Okay, and here we go. This is, I want to now, I spent a long time thinking about this, and I think I've achieved some new sort of clarity here. These four symbols that I've just introduced, which are in some ways totally intuitive, really three symbols. This is more of just a note, note that we should interpret concatenation of the null string in this way. So I have these three new symbols. It's really even two symbols, right? It's concatenation and using exponents to refer to a certain number of concatenations. This always produces, given a particular string x, these produce a particular new string. Okay, but then there's this other notation, which is a little bit vague, so I want to pause for emphasis. X star is 0 or more copies of x. Okay, what the hell does that mean? It's sort of vague, and x star does not specify a particular string. It's kind of a way of saying I either have no x's, or 2 of them, or 3 of them, or 4 of them, or something like that. The way Gossett writes it is that x star is some element of the set of all sort of powers of x. In other words, like I just said, right, x of the empty string, which would be x to the 0, or the null string, which would be when n is 0, or x squared, or x cubed, or whatever. So if you take all of them together, that's sort of the powers of string x, and x star is just one of them. So this is a sort of indefinite way of saying, I have some numbers of x, but I'm not telling you how many. It's a little, I think you just get used to it. And okay, here's another one. X plus is 1 or more copies of x. And so x plus is going to be some element of the set of all powers of x such that the exponent is greater than or equal to 1. Okay, and these are, I am now going to put a green box around these because they are in some sense like indefinite in that they do not refer to a particular string but refer somehow to a generic string or a category of string or something like that. Okay, can we do some examples? We can. I'm squeezing this crap in here right now. So here are my examples. So let x be the string AB, and let y be the string of length 1, which is just C. Okay, so what would x cubed be? Okay, well that's not that hard. It's just going to be AB, AB, AB. Okay, great. What would x squared y be? It would just be A, B, A, B, C. Okay, I think those are easy. What about x squared y cubed? Okay, well now, yeah, what's up with that? Well, this would be, well, just that 3 times, right? So A, B, A, B, C, A, B, A, B, C, A, B, A, B, C. Okay, and then the sort of last 2 that I guess I want to talk about is, what is x star? Well, I can't really say what x star is. So x star is the empty string, or it's AB, or it's AB, AB, or AB, 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 etc. So more specifically, we say that A star is an element of, and I can express this as, well, it's the precise language that we that we saw in the previous example was generated by our grammar. Okay, and all right, I've run out of room for x plus. Well, I'll just do it, I guess. X plus is now the empty string is considered not part of x plus. X plus is a b or a b a b or a b a b a b, etc. Okay. Good, 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 good. Okay. Now, and okay. Yeah. Good enough. All right. So leaving that up there, we also have an extremely similar notation for sets. I should really say sets of strings. Sets of strings. The previous notation sort of operates on strings, whereas this notation is going to operate on sets of strings. Okay, I'm going to try to write small. Let A and B be sets I guess it should be, well, yeah, let A and B be sets of strings, I guess is really what I want to say. Sure. Symbols or doesn't, okay, good. Whew. All right, then what is the concatenation of A and B? Well, the concatenation of A and B, remember A is now a set of strings. B is a set of strings. The answer is, it's all the strings, which are themselves concatenations of a string in A and a string in B. So it's all the strings of the form AB, where A is in A and B is in B. Okay. Whew. Good. What is A to the 0 power? Okay, well, that's just going to be the null string. You're sort of saying, okay, I'll just leave that there. What's A to the n? Well, again, I define this recursively. So A to the n is going to be A to the n minus 1 for n greater than or equal to 1. In other words, just like on the left, I've defined powers of a set of strings in terms of the sort of concatenation on sets of strings. Okay, and now I can be a little bit more precise about what A star is. So maybe this is the better way to introduce A star. A star is now going to be a specific set, but it's going to be the set of all the possible powers of A. So what is A star? It's the empty string, the null string, union A, union A squared, union A cubed, etc. So it's all possible. Well, I'll just leave that. Okay, and of course A plus, I don't know if I'm ever going to use this, is just A union A squared union A cubed, etc. Okay, let's do an example. I made a silly example. Here is my example. Suppose you're trying to talk about all possible curse words. Okay, so let's let A be, and a lot of curse words are like, you know, a good example of a curse word is like jerk face. So let's let A be the sort of adjective jerk, and the other one I put here was potty. And let's let B be face and head. Okay. Well, if A is jerk potty and B is face head, then what is AB? Well, AB is going to be the set of all strings which are concatenations of something from A and something from B. In other words, jerk face, jerk head, potty face, potty head. This is the best video. Suddenly this video became great. Okay, what is A to the 0? Okay, that's just the null string. That is or the set containing the null string, really. That's maybe the best insult of all, where someone's offending you and you just stare them down and just look at them and shake your head like, oh, no, 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 no. Okay, but I like to pronounce my curse words out loud, so I might be interested in A cubed. What's A cubed? Well, A cubed is the set of all strings which are composed of Well, what it is just A. Okay, but notice that once I write A cubed as A, then when I go to interpret that, it's all the strings which are themselves concatenations of 3 versions of something in A. So I'm now going to have 2 choices for this one, 2 choices for this one, and 2 choices for this one. So there are 8 things in A cubed. Jerk, jerk, jerk. Jerk, jerk, potty. Jerk, potty, jerk. Jerk, potty, potty. Potty, jerk, jerk. Potty, jerk, potty. Potty, potty, jerk. And potty, potty, potty are the 8 strings in A cubed. That was so much fun. Okay, what about A star? A star is going to be even bigger, right? This is going to be, it's going to have in it, of course, the empty insult, the best insult of all, plus you can have just one, you can just say jerk, or you can just say potty. So jerk, potty, jerk, 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 potty, potty, jerk, potty, potty. Then the insults of length 3, so to speak. You know, all the ones we just mentioned, and then ones of length 4, like jerk, 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 potty. All that's going to be in A star. Okay, and now, finally, A, B star. I personally find this to be very subtle, and find this to be a point of confusion for students and myself. What is A, B star, literally? A, B star, literally, is the empty string, union, A, B, union, A, B squared, which is A, B, A, B. You know, union, A, B, A, B, A, B, etc. You have to think about it kind of that way, right? We sort of define the star in terms of the union of powers, and then we define those powers as concatenations. But it really all comes down to concatenation. So if you consider the set ABAB, the set ABAB is the set of all strings which are composed of 4 concatenations, or the concatenation of 4 substrings, for which the first one is an element of A, the second one is an element of B, the third one is an element of A, and the fourth one is an element of B. In other words, you sort of choose at the end, not at the beginning. So it's very possible that the 2 strings from A are different. So one element of ABAB is, for example, jerk face potty head. And so what is this AB star? It's null string, jerk face, jerk head, potty face, potty head. Well, okay, I think we're done. Good. And that is the perfect place to pause, but this lecture continues. Maybe we shouldn't pause, maybe we should just push on. We're actually almost done. We have 2 pages left out of 11. All right. Pushing on. All right. Sure, we could do this somewhat faster live, but you know, don't want to leave anything out. Good. Okay. We are now going to make a regular grammar, which is its own kind of skill. Okay, so consider the following language. A to the I, B to the J, C to the K. And notice we are now using, as we will, our notation that we have just mastered for expressing powers of characters. So this is to be interpreted as, some number of A's concatenated with some number of B's concatenated with some number of C's. And I, J, and K have basically no restrictions. They can be 0 or not. Okay, let's try. So this is, I just took this directly from Gossett. I like kind of what he did here. He said, okay, first use the most, is things still recording? Sure it is. He said first use the most kind of simple, intuitive approach, which is, look man, first you're going to make some A's, then when you're done making A's, you're going to start making some B's, and when you're done making B's, you're going to start making some C's. So Gossett says, this is his own example, he says, okay, let S first go to sort of section A. So let's think of non-terminal symbol A as being the symbol that sort of captures the idea of we're in the A section now. And then what do I do in the A section? I just make some A's. And then I stay in the A section possibly. But then at a certain point I'm ready to leave the A section. And I want to go to the B section. And well, what happens in the B section? In the B section I make B's, man. And in general I might be hanging out in the B section for a while making a lot of B's. But when I'm done making B's, I leave and I go to the C section. And what happens in the C section? I make a lot of C's. And when I'm all done, I just close it all off with a nice lambda. Okay, I don't know how intuitive that was. If we were doing this live in class, I would have given you 5 minutes to think about this. But to me, this seems like a very intuitive way of writing a grammar for this language. And okay, so what's the problem? According to some definitions of regular, this is fine. But for most definitions of regular, and certainly for Gossett's, though this is a grammar, it is not a regular grammar. And regular grammars have certain properties, and so if it's possible to write a grammar as a regular grammar, maybe we should try to do so. And I hope everyone sees that it's these three rules in particular which have violated one of our rules about the production rules, namely that there must be at least one terminal symbol per production rule on the right-hand side. So that was attempt number 1. Attempt number 2 is going to therefore have to be a little bit more subtle. If I want to be able to make this to make this grammar regular, so I have to sort of bend a little bit what I want to do to fit the rules of the regular grammar. Okay, let's do it. What I'm now going to do is sort of think a little bit more strategically, because of course, though it might be the case, so basically I have to start from the beginning of this string. I have to think, okay, what am I going to do? Am I going to make some A's? Well, one thing I might do is, okay, hold on, how do I put this? One thing I might do is make one A and then get ready to make some, no, that's it, yeah. This says write an A, and because I have to write something per line, right? So I can't just go to the I can't just go directly to the I'm making A's now stage. I have to sort of do something. So I write an A and I go to the I'm making A's stage. You should really now think of capital A as the state of I just made an A. So in other words, make an A and go to the state of I just made an A. Is that right? Yeah, it is. Okay, but perhaps since I could be 0, there are no A's. And so I should also allow myself to go straight from the start symbol to little bb. And this would be the case in which your string had no little a's in it. And b being the sort of the state of I just made a little b. And then of course, also it's possible that there are no a's or b's if I and j are both 0. So I could also just go make a little c and go straight to the state of there being I just made a c. And then it's also possible that if I, j, and k are 0, then the string is null, and the null string is a string of this language. And so we need to be able to generate the null string, so I have another rule for that. Okay, and now, going back to A, well, what does it mean to be an A? It means that you just made an A. And now you have several options for what to do after you just made an A. Well, you can make some more A's, or you can say, I'm done making A's, and you can start writing B's. Or you can go immediately from making A's to making C's if there are no B's, because J is 0. So A could go C, C. And it's also possible that there are no B's or C's, and so when you're in the state of making A's, you might just end the string right there. That's if J and K are 0. Oh my god. Alright, well now what about B? Well, if I'm in state B making B's, I could make some more B's, or I could declare myself done making B's and make a C and go to state I'm making C's now. Or we could just end the string generation with a lambda. That would happen if there were no C's, so that K was 0. And then finally, when I'm in the state of I just made a C, I could just make more C's, and then eventually I'm going to end it. So, attempt 2 was sort of maybe a little bit more difficult, but surely you will see that this is a regular. I think it's very intuitive that this is the correct, that this grammar does generate all these strings, but more importantly, this grammar is regular because it meets all of our conditions for being regular. Finally, I will note that a language is regular if there exists some regular grammar that generates it. So just because this non-regular grammar generated this language doesn't make this language non-regular, because there existed a regular grammar which generated this same language. So we say a grammar is, or a language is regular if there exists some regular grammar that generates it. Okay. We now have 2 more examples. I'm now going to try to squeeze this in. I think I'll fail. Well, maybe I'll succeed. 2 more quick examples. Okay, here are the examples. So here we go. Example, this is still from Gossett. Let there be some, I don't know why he calls it T. Let T be A and B. And let's consider the following language L. L is all non-null strings of T star with no double letters. Okay. So in other words, you just can't have 2 letters in a row. So for example, A, B, B would not be a string of this language because there's this repeating A here. Can we write a regular grammar for this? I think we can. And we have to kind of just be a little bit smart with this, right? Well, let's start. What are we going to do? The string can't be null. So the first letter has to have some kind of length to it. And so either it's going to start with an A or if it's going to start with a B. But if it starts with an A, then I immediately need to be on high alert that the next string, the next character has to be a B. And so, well, okay, this is Gossett's notation. Let's go to AA, where big A is the non-terminal symbol, which kind of captures the fact that I just made an A. But the other option is that I could make a B. And if I make a B, then I go to B, big B, where big B is the non-terminal symbol that says I just made a B. But, of course, if an A came previously, then a B must come next. And so the only thing I can do is, well, I have 2 options. I can either make a B and then go to B, in other words, yeah, or I can just end the string at any given point. But since A is the state of I just wrote a little a, then I can't write a little a next. So there you go. And then the other one is exactly analogous. B can go to, if I just wrote a B, then I have to write an A next and go to the state of I just wrote an A, or end the string. And that's it. That's the example. Okay, final thing. I think I have 4 minutes or something like that to talk about this. Consider the following language, L, which is the set of all strings of the form a to the n, b to the n, with n greater than or equal to 0. Okay, so what's in this language? For example, a cubed, b cubed is in this language. But so is like a to the 100, b to the 100 in this language. And okay, I could give you a couple minutes to think about this and to try to come up with a regular grammar to generate, to generate this language, but you're going to have a hard time because the fundamental right branching nature of regular grammars is that I sort of write a character and then I sort of move my cursor to the right. I write a character and I move my cursor to the right. And I sort of never look back behind me at what's happened so far, and all I can do is look forward. And so somehow this grammar is not powerful enough to like remember, so to speak, how many A's have been produced. And so if you want this grammar to be able to generate like A to the 100th, B to the 100th, so 100 characters of A followed by 100 characters of B, I'm going to need a lot of production rules. I'm going to sort of need production rules which somehow generate A's, but remember in somehow via some creation of some exotic non-terminal symbols how many A's have been produced, so that when I finally get to the B generation phase of my derivation, I can make sure that they're perfectly matched. And I think the answer is that you just can't do this. And I think this is kind of intuitively clear, but we'll talk more kind of about this later, I guess. But this is a kind of a classic example of the sort of simplest language, which is just fundamentally not regular. And that is to say that regular grammars are powerful, but they are not powerful enough to do a lot of things. They're totally not powerful enough for studying the structure of natural languages, and they are even not powerful enough to generate some languages like this. And at the last week of school, we will look into some different kinds of grammars which are powerful enough to generate languages like this. And those grammars are more powerful because they are less restrictive regarding those rules that every regular grammar must follow. If we relax some of those rules and allow for more convoluted combinations of terminal symbols and non-terminal symbols, then we get to more powerful grammars which can recognize somehow more complicated languages. Okay, goodbye!